Welcome to Unit 14, Video 4, Reaction Rates. By the end of this video, you should be able to understand what a reaction rate measures, understand the relationship between the rate of consumption of reactants and the rate of formation of products, and understand how reaction rate varies with time. In talking about reaction rates, we're entering the portion of chemistry referred to as chemical kinetics. This is the area of chemistry concerned with the speed or rate of reactions. This is a very deep topic, and we're really only going to scratch the surface. As you probably know, a rate measures the change in a property over time. So for example, we can measure the distance we travel per hour. We call this the speed we're traveling. This is our rate of travel, 45 miles per hour. A reaction rate measures the change in the concentration of a reactant or a product per unit time. For our purposes, it's usually going to be per second. Another way of thinking about reaction rate is that it measures the rate at which reactants disappear and the rate at which products appear. Written as a mathematical expression, we can express rate as the change in concentration divided by the change in time, or as the concentration of A at time 2 minus the concentration of A at time 1 divided by time 2 minus time 1. Or most simply, as delta concentration of A divided by delta T. Recall that A is a reactant or a product, and brackets refer to its concentration. All of these expressions mean the same thing. We'll be looking at the one at the bottom because it's the most simple to write, but they all mean the same thing. Let's think about how concentration of reactants and products change over time. As you can probably imagine, when we begin a reaction, the concentration of reactants is very, very high because no reactant has been turned into product yet. Therefore, the concentration of products will be very low. But as the reaction proceeds, we see that the concentration of reactants, represented by the orange line, decreases, and the concentration of products, represented by the red line, increases. This is because as the reaction proceeds, reactant gets used up and turned into product, therefore decreasing reactant concentrations and increasing product concentrations. Notice here that the orange line says reagents. This is just another term for reactants. If we look at numerical data measuring concentration over time, here we have the reaction between nitrogen dioxide, NO2, to yield nitrogen monoxide, NO, plus O2 gas. Notice that here we've taken concentrations of each substance over time. Not surprisingly, at time 0, at the start of the reaction, the concentration of NO2 is relatively high, and the concentration of our products is 0. However, as the reaction proceeds, the concentration of NO2 will decrease while the concentration of NO and O2 increases. Furthermore, you might notice that the concentration of NO2 does not decrease at a constant rate, nor do the concentration of our products increase at a constant rate. This will become important later. Another important thing to take note of is that there's a stoichiometric relationship between amount of decrease of reactant concentration and increase of product concentration. You'll notice that when NO increases, O2 increases by half the amount. This should make sense since there's a 2-to-1 ratio between NO and O2. We should generate twice as much NO as O2. Therefore, at any given time, the concentration of NO will be roughly double the concentration of O2. Taking the same numerical data we just saw and graphing it, we see that the concentration of NO2, our reactant represented in black, decreases over time, while our concentrations of products, NO and O2, represented in blue and red, increase over time. You'll also notice that the rate of increase of NO is more than the rate of increase of O2. Again, this is because for every 1 mole of O2 formed, 2 moles of NO will form, based on our balanced equation. Again, you'll also notice that our reaction rate is not constant. If it were constant, we'd have straight lines here, but instead we have curves. In other words, the concentration of our reactants and products does not change by the same amount per unit time. Instead, you'll see that the change starts to slow down as the reaction proceeds. This should also make sense based on collision theory. As we make more and more product, there's less and less reactant to react. Therefore, the reaction will naturally slow down. There's fewer reactant molecules to collide with one another as the reaction proceeds. As suggested by our numerical data and that same data on the previous graph, there's a relationship between the rate of formation of products and the rate of consumption of reactants, and it's based on the reaction stoichiometry, or the balanced equation. So if we express the rate of consumption of N2 in terms of the rate of consumption of NO and O2, you see that we get 2 times the rate of consumption of NO2 is equal to 2 times the rate of production of NO, which is equal to the rate of production of O2. This matches our stoichiometric ratio. Every time 2 molecules of NO2 are converted to product, we get 2 molecules of NO and 1 molecule of O2. Written mathematically, we can say that 2 times the change in concentration of NO2 divided by the change in time is equal to 2 times the change in concentration of NO divided by the change in time, which is equal to 1 times the change in concentration of O2 divided by the change in time. Notice here I've put a negative sign in front of the consumption of NO2. This is to represent the fact that NO2's concentration will decrease, while the other 2 will increase. While these expressions are useful, they prove problematic because remember that rates vary with time. They are not constant. Therefore, if we choose a time interval at the beginning of the reaction versus a time interval at the end of the reaction, we'll get a different value for the rate of the reaction. This proves problematic, so instead, we look at something called the instantaneous rate. For those of you who have taken calculus or pre-calculus, you might have learned about instantaneous rates. If you haven't, don't worry. You'll get a little preview here. Since the rate of a reaction is not constant, the average rate is not very useful. Imagine we graph our reaction rate here as shown by the black line. If we measured the slope of this line, it would vary over time. Therefore, the rate of this reaction would be different at each time interval. So taking the average rate doesn't really tell us much. Instead, we take the instantaneous rate. This might seem like a strange thing to think about, since instantaneous means a single point in time, and rate measures the change over time. But mathematically speaking, we can make this happen. Instead of measuring the rate over the entire course of the reaction, instead, we take the rate at one single point in time. For those of you who are interested in the math here, this is equal to the slope of the tangent to the curve at that point in time. So taking a look at the blue triangle at the top of the graph, we see the red dot representing the point at which the tangent line meets the curve, and we can measure the slope of that tangent line and generate a rate at that particular time of 5.4 times 10 to the negative 4th mole per liter for each second. In other words, at that moment in the reaction, 5.4 times 10 to the negative 4th moles per liter will be converted to product every second. Notice down below at the green triangle, we have a different rate because the slope of our line is no longer the same as it was at the blue triangle. Here, the red dot in the green triangle, again, represents the point we're taking the tangent to. And if we take the slope of the tangent line from the green triangle, we get a different rate, 2.7 times 10 to the negative 4th moles per liter for each second. In other words, at that point in the reaction, 2.7 times 10 to the negative 4th moles per liter will be converted to product every second. What's important to note here is that these rates are not the same. In the next video, we'll talk about how to generate instantaneous rates that are useful for measuring the rate of the reaction over a longer period of time. But for now, it's important to realize why instantaneous rates are important and why the rate varies as the reaction proceeds. That brings us to the end of this video. Let's review our goals. First, we looked at what a reaction rate measures, the change in concentration of reactants or products over time. Then we looked at the relationship between the rates of consumption of reactants and the rates of formation of product. Recall that it's stoichiometric based on the balanced equation. And finally, we looked at how rates vary with time. The rate of the reaction is not constant because as the reaction proceeds, we have less reactant to form product. Therefore, the reaction tends to slow down.